Okay, welcome everyone to this week's CHIME FRB Journal Club. We are very lucky to have our external speaker for today, Clancy James, who is going to tell us about some of his recent papers about FRBs and source counts and things. So I will hand it over to Clancy.
Okay, thank you very much, Emily, and thanks for inviting me all. Let me share my screen. So I must admit that in giving this talk, I'm well aware that you're all privy to a bunch of knowledge that I do not know. So it's going to be, and normally if I was giving this in a room, I'd be all sort of, I'd be looking at your reactions to things to see whether I get knowing nods or, you know, sort of head and hands. Oh, I can't believe he's so stupid. He doesn't realize. But maybe we can get some hints towards the end and see how we go. So, okay, this is the work on FRB population modeling, which means it's probably the most boring FRB talk you're ever going to hear because, it's the modeling. It's not the usual FRB talks of, look, here's a weird burst and here's another weird burst and here's a beautiful image of a host galaxy and we don't know what it means, but look at it, which is how I sort of characterize most of the FRB field. And this is sort of work done with a bunch of others. I must admit that mostly this was me going headlong into the modeling myself because that was sort of my background, and then pinging other people for various contributions. So let's sort of dive right in, since if you aren't familiar with FRBs by now, I'll skip all that intro and I don't know what collaboration you're working with. I assume that's correct, Emily, that everyone here is with CHIME FRB and
Yep,
got it.
that's right.
So this is how I would sort of characterize the first population study of FRBs, which would have been this plot in Shannon et al., which at the moment, you know, in hindsight, looks all very obvious and easy to understand. But at the time, you know, we spent a long time discussing. And so essentially you've got the assumed extragalactic DM on the x-axis, which was simply the DM minus about 100 minus any 2001. Y-axis is Jansky millisecond power. If you assume an approximate 1-to-1 DM redshift model, then this gives you redshift up here. I will very much get back to this one later. Just to skip ahead a little bit, this point absolutely will not be at a redshift of 1. It'll be more like down here, but anyway. But the main point is that you have the Parkes in black. I have no recollection of what the magenta and cyan points were. And you see that Parkes DM is higher than ASKAP DM, but it's a lower fluence because, you know, ASKAP was a wider, broader survey. And then this is a clear case of, obviously, DM is a tracer of distance because Parkes is seeing deeper into the universe. FRBs must come from a distant population, is not consistent with, you know, something in the local universe that's just been, you know, has huge excess DMs for whatever reason, right? And, you know, you can also then say, right, burst energies get up to 10 to the 34 ergs per hertz. At the lower end, you could either say, well, maybe there's a lower energy cutoff, or maybe it's just that we only probe such a small volume of the local universe, we don't see anything. And you kind of then start to ask questions about 121102, and naively you immediately say, oh, well, clearly this looks like it's from a different population and is different and weird. I'll come back to this point maybe on the second to last slide. But for the moment, because the points I'll be modeling in this talk will be from ASKAP and Parkes, I'm going to be sticking to the single burst case and looking at this sort of population here and then seeing how effects from maybe things that repeat and emit many bursts of lower energy would affect that. So, okay. One of the key points here is that there's a lot of papers that look at FRB population modeling, which answer questions like how bright are they, how many are there, do they evolve with redshift, is this consistent with single or multiple populations, and out to what distance do we see them? But there's also this sort of subset of FRB papers, you know, on how much mass, you know, FRB cosmology, right? How much mass is in the universe? What's H0? Where is the gas? And in a different font for some reason, in a different font size, where did he reionize? Maybe that was a appropriate thing. And one of the points I want to get out of that is that in future studies, these should be addressed simultaneously in the same work. Essentially to cut ahead, because this governs your distribution of dispersion measures, and your dispersion measure is a biasing factor in answering these questions. And it's just a question of what do you really care about as to which one of these two you see as the biasing thing and which is the thing of study. So, okay, if you want to model the FRB population, I think that, a simplest model is you have to have some burst energy distribution. And the two simple cases are one from a power law from Emin to Emax with some cumulative, with some slope, right? I always deal with the cumulative slope, the number of bursts above some threshold. And that, for 121102, that cumulative for a single source, right, that might be about -1, the cumulative slope, so differential slope -2. A lot of people like the Schechter function, which is basically this with an exponential cutoff. If you do like this Schechter function, please ask me about it later, and I might go on a rant. But for the moment, I think it's an arbitrary choice. I'll just be using this. Then you might say, well, maybe these things evolve with redshift, and the way this was sort of done by JP and Ron and a couple of their papers is simply take some model of the star formation rate and scale it by a factor of n, to the power of n, right? So n equals 1 means scaling with the star formation rate, n equals 0 means a flat population distribution, no evolution. And you can imagine, I think the AGN population is even more peaked. So that's sort of like n equals more than 1, but it's a poor model. And then, of course, spectral dependence, right? Oh, that should be, yeah, that is to the alpha, right? So how do things vary with frequency? Yep, as I mentioned earlier, I'm going to be modeling the burst population, not the progenitor population. And so if nothing repeats, it's the same thing. If they do repeat, clearly it's different, but we'll get back to that. So one thing I want to point out is there's this sort of subtle nuance. So again, until the CHIME data becomes public, the best info we have on the spectral dependence of FRBs comes from JP's paper using 23 ASKAP bursts and finding that there's some preference for more power at lower frequencies, which is, what you find from modeling this plot. Now, the trick is, of course, that if you say FRBs have some spectral dependence, that applies if they're an intrinsically broadband thing, right? If they're intrinsically broadband, wide burst, okay, sure, they might have some random modulation on top that we don't understand that might come from weird source physics or might come sometimes from, scintillation. But clearly, if you look at some of these bursts, Law et al. Paper from 121102 bursts saw things of order 500 megahertz bandwidth, or this one that we saw with a Parkes repetition with 50 megahertz, right? What's the spectral index of this, right? Like if you take, if this is the classic test of that, if you have a student who fits a power law spectral index to this, you give up on them, right? So in that case, the interpretation would be that this reflects a band, you have band limited bursts with a frequency dependent rate, right? So the rate varies as a function of frequency, and then, you have band limited bursts that sit in narrow frequency bands. Now, to first order, it turns out that if you've got a pure power law with no maximum energy and you ignore the K correction, these two models are equivalent, right? They're linked through the cumulative source count slope gamma. So with gamma of -1, then it's all the same. But because of maximum energies and because of K corrections, your choice of these two models does affect the results. So I'll inevitably show results, I think, for the first case, but at some point I'll return to the second one and say, well, look, numerically, the results do depend on that. And clearly, the spectral dependence of FRBs is more complicated than either. So, but I think showing results for, a broad bandwidth versus narrow bandwidth things is a reasonable sort of bracket to look at. So, okay, if you want to do this properly, of course, you've got your intrinsic model of the FRB population, and then you've got to account for obscuring effects. So actually looking back in the literature, I think, Emily, your paper with Evan on the fine how you get DM sensitivity effects with different burst searches was one of the first papers I saw in the FRB literature looking at such biasing effects. But I think at the moment, all search algorithms that are used, they do clearly have different biases, but they're relatively small. So those sort of fine effects where you might get plus or minus 5% in sensitivity because the burst DM doesn't quite line up with your search DM, sort of ignored, and that sort of random noise there. But what you clearly have to do if you want to include key system response factors, you need to account for the beam shape, right? The fact that some parts of your telescope's more or less sensitive to some different parts of the sky. So this is the Parkes multi-beam beam shape here. You need to account for the fact that either FRBs that are intrinsically wide or FRBs that are have significant DM smearing, more difficult to detect. So there's actually an interesting story here. Before Shannon et al. Nature paper, I was supervising a third-year student, and I noted that no one in craft had actually done a check of the FREDA search algorithm to check it was doing what we expected. So I had this third-year student, Mawson Salmons, do that as a project and basically write up a simplified Python version of what FREDA was meant to do. So in the meantime, Shannon et al. Gets submitted to Nature, and the referee comes back saying something along the lines of, "Have you checked?" Right? And so Mawson was able to say, "Yes, we have," by throwing this in getting a Nature co-authorship while he was just about to start honors, which was a nice way to begin. It's a good student too. But when he presented this at an intrinsic craft meeting, he did a test of this on some pulsar calibration observations, and he got this beautiful alignment of what FREDA was doing with his simplified Python. We all understand it because it's Python code kind of thing, and they matched beautifully. And so Mawson presents this as saying, "Oh yeah, and I see that my undergraduate work is correct because it, replicates what FREDA is doing." And then Keith Bannister, who wrote FREDA, his immediate reaction upon seeing it was like, "Great, FREDA's working because it matches what you did." So it was sort of that's cool. Okay, I'll stop going on little side notes. The other thing, of course, that you need to care about is that if your dispersion measure smearing affects your sensitivity, you care about what your distribution of dispersion measures is, right? And so, we now got this thing. I don't know if you guys have adopted the terminology of Makar relation, but we're using it in craft for this general one-to-one DM as a function of redshift relation. But clearly there's a lot of smearing here because we know, right, that the mean should be a mostly straight line here. But if you just took away this guiding line, right, and you looked at these colored points, it's not really clear that a straight line fit would be the right way to do it, right? You sort of maybe treat it as a Gaussian coming up. So, so clearly there's a whole bunch of scat. This has got an excess DM. These are, low DMs. I forget. This is probably 1211. Is that 1211? No, that's 121102, right? I forget. And this is, yeah, okay. I forget why this is in gray, which localization it was. But okay, so you've got to include that. So as far as I'm concerned, before this, the only published sort of application of doing all of this properly, right, is by Lau et al. Oh, and I should note, by the way, that the full approach, you've got to model your physical truth, model your system response, repeat this for many potential truths, right? Iterate over all possible cases of this that you can think of, and then compare with measurements and work out, well, what range of this matches your measurements, and hence, make inferences about that, right? Because there are a bunch of papers, I think it was probably a paper by Manisha Caleb et al. That first included all these different biasing effects, more or less, right? Some models. But they didn't then go on and iterate over possible physical truths. It was more like, okay, let's take a single guess at this. For that single guess, what might we see? And of course, that then doesn't tell you, well, how good your guess was. So Ray Lau and collaborators published this paper. See Duncan getting in on that, getting in the action here fairly recently in M and RAS, where they basically took a sample of bursts by various instruments. They looked at Emin, Emax, and slope of the FRB luminosity function. Also looked at the mean and spread of the FRB width distribution and the absolute number of FRBs. They fitted six parameters there. And they did that fit to this sample using a Bayesian approach here, right? And so these are their key results. They got a pretty good fit for the Emax energy. I've converted them to the units I'm looking at. The differential slope was minus 1.79, so that's actually pretty flat. And something about 5,000 per cubic gigaparsec per year above 10 to the 40 ergs. That should be ergs, not ergs per second, sorry. So, so they did what I consider to be, the currently published application of FRB population modeling. And I think that where the field's at a stage now where there's a lot of papers out there where they kind of say, oh, we use a 1-to-1 DM redshift relation and we assume this and that. And I think we're beyond that now. So if you're refereeing papers where they make a whole bunch of assumptions and they say, therefore, FRBs truly behave like ... please reject it. Where the field's moved on. That was fine, I think, for a few years ago. But now we're beyond that. We should have better standards. So, okay, I've just said they did a great job, so why continue? So let's try to see what improvements you can do. Well, first of all, you can improve your beam shape modeling, as I'm sure everyone in CHIME knows it can be important, right? We've now got an inclusion of localized FRB, so you can use the measured redshift, which is not part of Ray Lau's paper. You have your measured signal to noise ratio, right? That can actually be a parameter that you use in the fit as opposed to just the DM. You can then say, well, we've talked about cosmological DM, so you can use a full model of the cosmic DM distribution. So if this is redshift and this is your cosmic DM contribution, this is your probability of DM given redshift that was used in the model from JP's recent cosmic baryons paper. You can also probably should include your host galaxy width distribution, right? Fit some model of what your host galaxies are doing and allow that to vary freely. And you also want to do a bit more control as to which bursts are in your sample, right? So for observations in Parkes like HTRU and Superb, they were clearly, and also CHIME would clearly apply here, right? Where you say, right, we're going to look for FRBs. We're going to spend this many thousand hours on the sky, and we're going to report our results. And you know then that if you don't see anything, then those results get published, right? Like there were no bursts observed in the low latitude HTRU sample, right? But we know about that because I said we're going to look for FRBs, and when they didn't see them, that was still published. However, for a lot of observations where, from telescopes where only one FRB was seen, or maybe it was here and there, there's a lot of Parkes FRBs, for instance, which have been published from other observations where we know the time that the observer spent looking, but what we don't know about is all the observations where someone was looking at a random object and didn't see an FRB because no one bothers publishing that. So this kind of work, I was supervising Freya for an honours thesis, got these guys to contribute to the DM distribution, and we took a closer look at the Parkes beam shape, including an improved model from Alex. So Keith Bannister's model for the Parkes beam shape was used in Vedantam et al. His paper with Vikram Ravi and Ryan Shannon trying to reconstruct Parkes, the directions of strong Parkes FRBs that were seen in multiple beams. And then this model was called into question in a paper by Ron and JP at some point. And then the question was, well, how important is it? So, and the other thing is I want to limit this in scope, right? So I'm not going to be varying this cosmological DM distribution and focusing on the FRB parameters, but I think in future, this is going to be jointly fitted. So the other caveat I must have to say is that, so this is being refereed and I've made corrections. Referee made a comment along these lines, make sure you put in this 1 + z time dilation of the rate. And then my response was, yes, of course this is in there. And yeah. Turns out it wasn't, because the code that I'd imported from a previous paper had this time dilation factor in a different part of the code that dealing with repeating FRBs that wasn't imported. So yeah, now so the results have been updated for this stupid error, but the archive papers haven't been yet. That's my to-do for the rest of the morning after I finish. So if you're working off the archive papers, qualitatively the results are the same. Turns out that when you include this, the results become more significant. So that was lucky. but you will see some things that don't quantitatively match. Okay, so first thing, before we get onto the juicy results, is some conclusions about what correct modeling means. So you need to fit, your sensitivity depends on the width, and when you fit the effective width, you might include something like an intrinsic width, scattering, DM distribution, and your sampling time, right, as an effective width. Here, I don't distinguish between the scattered width and the intrinsic width, right? Even though you might imagine that you expect more or less scattering from, that should be correlated with DM, right? So, so the reason why I don't distinguish between these two is simply because the scattering that you expect from the IGM is expected to be minor, right? And we don't see, okay, and this is part of the talk where you might be nodding sagely or no more. You don't see strong correlations between scattering and DM, at least in data so far, which suggests that most of the scattering comes either from the source or in theory locally from the Milky Way, but probably not, right? And of course, the source scattering decreases with redshift, but then that's going to be cancelled out by the fact that, DM smearing becomes more significant, right? So that essentially means that you can I think you can fairly legitimately get away with just modeling the total incident source width and having it be redshift independent in the model. At least I think it's good enough, we'll see. And I use a log normal distribution for the distribution of widths because that doesn't seem to be too bad, but it's not going to be correct, right? A lot of the high width distribution won't be probed. So thankfully, Lau et al. Found that the modeling of the widths is relatively uncorrelated with other parameters. So this is simply the two-dimensional correlation plot of width parameters on the x-axis and other parameters on the y. And you see there's no, horizontal, there's no diagonals here, right? It's one-dimensional, which means that you can get away with guessing your true model parameters, fitting the width distribution, and then checking later for your final fit, and it turns out to be fine. And so essentially what happened is that for another paper, Wayne Arcus et al. Did a fit to ASKAP and Parkes width and got a log normal distribution, which is the black line, right? But that was not accounting for these biasing effects. So when I have a physical truth of the blue line and then take into account various biasing effects, I get back to the, you turn the blue line into this green, orange, or red line when you fit Parkes and ASKAP observations. And then when you renormalize these ones, they both approximately match the black line, right? So if this is what you're measuring in black, the physical truth is more likely to be blue, but we don't have a good handle on the very wide side here, right? For instance, ASKAP observations, we actually stop. We don't actually search for things wider than about 15 milliseconds, for instance. But as you see, we don't expect to see many things out there because of this strong biasing effect. Although I know Utmost has a burst out at 30 milliseconds. I don't know what actually out of interest, is there some width beyond which CHIME stops searching? What's the maximum width that CHIME looks for FRBs? Someone to quickly pipe up? Oh, tell me later. I'll keep going in the interest of time. So the other thing is that you can say what the effects of the assumed width distribution are. One thing I'll just point out is that you can say the four cases I look at here are either assume that there's no width and that you all have intrinsic width of 0, which gives you, you can normalize to a rate of 1. Then if you use the observed width as the true width, right, then you say, oh, you're missing about 50% of the burst, right? So this is the observed width being used as a true width done in Wayne's paper. And then the fitted width, right, the fitted full log normal distribution means that you're missing 60, 70% of the burst. But then you can say that if you want to put this into a model, that's annoying because you have to integrate over this distribution. So I simply use five single points in width, like put a point there, point there, point there, point there, point there. And that numerical approximation turns out to be good enough. In fact, and then you can say, okay, what's a biasing effect in, say, your expected DM from this model? And it turns out that any of these three cases, using your observed width as a true width, the full distribution or a numerical approximation, you get about the same expected DM distribution, right, for your mean DM. So really, as long as you have a reasonable attempt at modeling your width distribution, it's probably good enough, is the conclusion. And clearly your assumed width distribution very much affects how many FRBs you're missing, right? But we don't really probe that space anyway, right? Because of these biasing effects, we don't have a good handle on how many FRBs are right out here, right? So I would take this log normal model in this range to be, take it with a grain of salt, right? It's just sort of an example, but it doesn't strongly affect the rest of the fits. All right, the other thing you can do is you can say, well, what about this beam shape modeling? So this is what I would call.
Can you hear me?
Yes, certainly can, Vicky. Go ahead.
Oh, sorry, just very quick question. And the highest width is I think 128 milliseconds, or it's on the other order of 100 milliseconds. It's a little further.
What you see in CHIME, is it?
Yeah. Although, I mean, it doesn't mean we have uniform sensitivity out there, which we certainly don't. There's a lot of RFI events.
The fact that you see something out there says that this log normal distribution is, well, I mean, okay, you're probably you're out to what, about 3 to 4 sigma, right? Because you've got of order 1,000, few thousand bursts by now. So a few thousand gives you what, about out to 3.5 sigma or something like that. So maybe.
Well, you asked what the maximum we were sensitive, maximum we searched to. So that was just.
Yeah, no. So I guess what I'm trying to do in my mind is say, okay, how wrong must this be here to reproduce something at around 100? But because it's log normal, I mean, even though it's got a mean of about 5, and this is a spread in ln space, so this is, I guess, that's only, actually no, that would be almost consistent, but once you take into account biasing effects, it's probably not. So, okay, that's interesting.
Yeah, but remember what Vicky answered just now was how far out we search. She made no statement about.
Oh, search. Oh, I'm sorry. Sorry, I thought that was the highest observed one.
No, that's the highest searched for one.
Okay, apologies. Yep, right. Okay, got it. Thanks.
But actually, so that was just, an incidental point. But then also you're emphasizing the high width. What about the low width? Because your log normal, plummets at low widths where actually there's biases also because the time resolution of surveys. So I'm a little confused by that.
Yeah, so this is something that probably needs to be updated after for the ASKAP and so for our ASKAP high time resolution plots. So this fit that was done by Parkes et al. To produce the black curve, that was before we'd included high time resolution ASKAP work. But keep in mind that what's being fitted here is the width, the scattered plus intrinsic width. So scattering is in here. And when we look at our high time resolution burst with ASKAP, we see that there's been one with a width of about 100 milliseconds or maybe 2 with those kind of widths of around 100 milliseconds.
Do you mean 100 microseconds?
Yes, I do mean 100 microseconds. 100 units that I would get right if it was a different time of day. Yes.
Okay.
100 microseconds. So yeah. So maybe this black line should go a little bit further to the left. What this really affects is, because I'm modeling ASKAP and Parkes here, ASKAP has a time smearing typically of a millisecond. So you don't care about this part of the distribution. For Parkes, you do care about it in the near universe. So, because clearly once DM smearing takes over, you don't care for sensitivity purposes if the intrinsic width is very low or not. So really this part of the distribution that's that's in the few hundred microsecond range, if there's more of them that are very narrow, then that will imply Parkes should be seeing more in the very nearby universe, which then means that if I've gotten this model incorrect and it's incorrectly underestimating the amount, so the truth should be more in the nearby universe, it means when I do the fits, it should in theory skew things so that the true population, I'll be trying to push more of the population, right? If I think the intrinsic distribution is lower and Parkes is actually more sensitive to that, given a fixed number of observations, it'll be biasing thing, it'll be pushing the population to the nearer universe, which means the effect of me getting it wrong would be to have less source evolution and a steeper source counts, right? Because the steeper the source counts, the more you would expect in the nearby universe. So that'll be the effect of a slight bias there. I don't think it'll be large though, because your nearby universe sensitivity is will be mostly fitted by ASKAP results. But okay,
thank you.
All right. Remind me what the total time is, because we're
we have about like 20 minutes left.
okay. All right. What I'm going to do is we'll mention beam shape modeling here, because this is probably relevant to CHIME. So I would say the 3 orders of beam shape modeling are to either use a simple, you see a full width half max of the sky at your full sensitivity, right? Or you model it as either a Gaussian or Airy function, right? Or you use your full beam shape. And when you're in this business, if you don't care about repeaters, then you don't actually care where your sensitivity is on the sky. All you care about is modeling how much of the sky you view at a given sensitivity, right? That's, so it's sort of like an inverse beam shape, how much of the sky you see to any given sensitivity. And that's kind of nice, because in those units, a Gaussian gives this as being constant in D log B space. So if you take these 3 parameters, what this really looks like is here is your beam sensitivity B, and here is your distribution of omega B d log 10 of B here. And if it's a Gaussian fit, right, it's a flat line, right? It's a constant. Now, when people do Gaussian fits, what they typically do is take your central beam sensitivity and apply that to your whole field of view. And we know Parkes outer beams are less sensitive than that. And we also know that the craft FRB, the craft sensitivity, the beam shape falls off with distance from center. So that's so this is what you would get from a Gaussian fit. These lines here are your full beam shape to within sort of numerical errors that we measure. These points here, these crosses, are what you get if you use a simple full width half max times number of beams times characteristic sensitivity. And then because modeling a full beam shape is annoying, I use a numerical approximation where I take just a finite number of points and model that. And you'll see that with ASKAP, there's a huge difference between the naive Gaussian approximation and this, simply because the ASKAP beams overlap, right? They overlap at the half power point. So you get a lot of the sky out to here, but then they begin to overlap at half power. And so you reduce how much of the sky you're sensitive to. Whereas Parkes, it looks approximately flat, but because the outer beams, 12 of your 13 beams are less sensitive than the standard assumed beam sensitivity, this gets you less sky at any given sensitivity. So how does this actually affect your modeling? Right, so complicated plot number 1. Blue ASKAP fly's eye, orange ASKAP ICS Parkes multi-beam, right? First, let's look at the green lines. This dash line is when you use the full width half max approximation. The other 3 are when you use either the full beam shape, a Gaussian approximation, or this numerical approximation to the truth, right, to speed things up. And these have all been normalized, the probability of Z in arbitrary units, so it's been renormalized. So clearly the Gaussian beam, it overestimates your rate. But the redshift distribution you might infer, and this is for my best fit model, which we'll get to later, so I'm just jumping ahead. It turns out that for Parkes, the Gaussian approximation is fine, right? It gets your absolute rate completely wrong by a factor of 100%, but your redshift / DM distribution is fine, right? So, okay, great. And if you use your full width half maximum, well, you get it wrong as you overestimate your sensitivity to the distant universe. In the case of ASKAP, in either orange or blue here, this one that gets it, so the solid line is correct, and your dotted line is this numerical approximation, and they both agree. But if you use your full width half max approximation, you overestimate your sensitivity to the, well, okay, not as distant, but still some distant universe. But if you use this Gaussian approximation, you overestimate your sensitivity to the nearby universe, right? Because of the overlap effect. So, for instance, Ray Lau's paper uses Gaussian beam shapes also for ASKAP. and that gives a significant bias in the opposite direction, right? So you have to be really careful how you model your beam shapes. And the good news here, though, is that in the case of parts, Gaussian beam shapes for this purpose are doing good enough, right? Okay, you overestimate your absolute rate, but in modeling your DMZ distribution, it's fine. So clearly with CHIME, if you care about repeating FRBs, which you obviously do, where you care about where in the beam things are as a function of time, then your precise beam shape will matter. But if you're only caring about, you know, that non-repeating population, and I hate that phrase, then maybe you can get away with a fairly approximate beam shape estimate for the purposes of your average sensitivity to the scale. Maybe. Again, probably not because of repeaters. So that was the conclusion of beam shape. I'll skip over that. Okay, so the data I'm using is ASKAP fly's eye, 24 burst here, ASKAP incoherent sums, so localized FRBs, where you get redshift, DM, and signal to noise ratio. Here you only get SNR and DM, and 20 parts multi-beam things. And so these are the basic parameters of each of the survey: the beam shape, the detection threshold, and your time frequency resolutions. And you need to control for galactic latitude. So I do not include observations where we're looking deep through the galactic plane, simply because you've got to recalculate everything for, technically, all the calculations depend on your local DM contribution, and having to redo that for pointings that went through the galactic plane are very annoying. And also, as I mentioned before, control for the reporting bias. So these samples here are subsets. Well, yeah, these two are subsets of all the bursts. And this one is simply, I'm only using the localized FRBs that were taken in L band, because we've got we've got a few that were at lower frequency and different time resolutions, and it just wasn't worth the bother, to be honest. Okay, and so the kind of calculation you do looks like this. This will be the only, well, actually, technically there's been other equations, but not really. So this is, you want to estimate the number of bursts you see. So it's simply observation time times the expected rate. That does not work if it's a repeater where you get weird bursty things in non-Poissonian distributions, but okay. The expected rate is, well, you need to integrate your source evolution over redshift, right, with standard cosmology thrown in. Depending upon where you sit in the H0 debate at the moment, your definition of standard cosmology might be different to mine, but okay, take something that's not too bad. You need to care about integrating over your telescope beam shape, right? How much of the sky is here at what sensitivity. Then you need to work out what fraction of your intrinsic luminosity function you're sensitive to, which is a function of your detection threshold, right? But that detection threshold depends on where you are in your beam, the FRB width. Obviously, if this is the intrinsic function, you know, your redshift and your DM, so you need to integrate over your burst width distribution and your DM distribution, right? And then you do that integral in some annoying numerical Python thing that takes up way too much computer time, but you'd be thankful for NumPy optimization. And then you can get an expected number of FRBs in an observation. And you can clearly also calculate, you know, your probability of any given DMZ by just, you know, taking out these two, the DM and redshift integrals and measuring the integrand. And if it's unlocalized, you can integrate over redshift, but not DM to get partial distributions. And then if you have a measured DM and or redshift, well, not or, DM and potentially redshift, you can get your probability of any given sort of signal strength, which is the ratio of your measured signal to noise ratio divided by your threshold signal to noise ratio. So I've sent a few emails to different people in CHIME asking you to please publish the measured signal to noise ratio and the threshold signal to noise ratio. I'll ask again nicely, please. It's important for stats here, but we'll see. Okay, so what do we get? Well, the first thing you get is that we can't fit strongly for spectral index, right? So what we've got here is a one-dimensional fit for this spectral index alpha as a function of, and this is your measured sort of maximum likelihood here. And blue is, okay, we see a trend for preferred steep spectral index, but you have very weak resolving power on it because all these observations are at 1.4 gigahertz and there's a strong degeneracy with source evolution via the K correction, right? So here we have your preferred value of your redshift evolution scaling from no evolution to, I don't know, some ridiculous thing that goes star formation rate to the power of 5. And as you get to a steeper and steeper, so this is minus 2.5 is strongly favoring low frequencies, and 0 would be no frequency dependence. And you see that there's this broad degeneracy there. So what you have to do is take this prior from JP's paper that I mentioned earlier, which is about a minus 1.5 plus or minus 0.3 is your Gaussian prior. So and what you see in follows, blue will be no prior on alpha, and orange will be using the priors from JP's paper. So no, we can't fit to the spectral index here. All right, so what about Emax? So essentially, you get a very good minimum Emax. So the reason there's no points to the left here is because they just plummet to impossible, because there's a localized FRB with a measured luminosity of about 10 to the 41.4 something, 0.4 something ergs. And when I say energy, this is at 1.4 gigahertz, assuming 1 gigahertz bandwidth, right? So you can convert from ergs per hertz to ergs, assuming 1 gigahertz bandwidth. And so you get sort of, a broad tail in your preferred Emax. And if you're into modeling FRBs, you probably care about this for emission mechanisms. And if you're not, you don't. And if you compare this to different estimates, Wayne's paper used a very high value, but we broadly agree with estimates from Lau et al. The other people who did it properly. This is the best fit value here, 10 to the 41.84 and so on. Now, I don't use a Schechter function. These guys do. When I did some tests with the Schechter function, you get equally good fits, right? It's just that Schechter functions take longer to evaluate. And even though I've had comments from plenty of people that, of course, a power law with a sharp max cutoff and sharp min is unphysical, yeah, probably it is. But a Schechter function is not well motivated anyway. So if someone wants to use a Schechter function, go ahead. I told you I wouldn't rant about this, but I am anyway. Feel free to go ahead and use a Schechter function, but it's no more or less well motivated than a straight power law. And whatever you do, don't think that because you're using a Schechter function, you're using a well motivated function, right? So no matter which of these two choices people are using, they're equally arbitrary, could well be very wrong, almost certainly are wrong. So still keep putting up your hands and say, are you sure that's the right function, right? So, okay. But the point is that given current FRB measurements, we have absolutely no resolving power between these two, right? They give equally good fits. So it's a non-issue from an empirical perspective. And I think with FRBs, I hope we can all agree we should be motivated empirically by what we see, because we have not been very good at getting the truth up until now. So, okay, what about this source fits to the source, the slope of the source counts distribution, this function gamma? So I'll warn you that I use the cumulative distribution gamma, right? So it governs the probability of energy greater than the threshold. So the magic numbers here are minus 1.5 gives you an equal rate per log bin in distance for a Cartesian universe. A slope of minus 1 gives you an equal rate per linear bin, right, in distance for a Cartesian universe. And this minus 0.9 is an approximate slope of the burst of 121102, right? Although I do not think the fast measurements of 121102 are out, and they clearly see structure in there. So you'll see that I get a bit best fit value that technically doesn't rule out values less than minus 1, but it does prefer a steeper distribution here. And what that means is that because you have something steeper than minus 1, you do actually expect a preference for an excess of FRBs in the local universe. Now per linear bin, right? But we'll see that later. So it means there could be an excess of FRBs near 0. And I suspect this is borne out by the CHIME FRB. I forget which NGC galaxy it was, but I think there's a good chance that a bunch of CHIME FRBs do come from the, within 100 megaparsecs would be my guess. Which ones? I don't know, please tell me. But that's going to be my bet. But it's a bet at 90% confidence. It's not a bet at 99.95. The other thing is to note that because this is steeper than these slopes, you can't simply take all repeating FRBs in the universe that look like 121102, stack them on top of each other, and because that would give you back the same slope. But quite clearly, if other things have changing maximum energies, then you can stack something like this and more like this and more like that with a cutoff, and you can get something that's steeper. So, okay. Now, oh, wait a sec. Did I skip over something? No, I didn't. Wait a sec. Oh, yeah. One thing I just wanted to note is that when I mentioned this excess near, because it's steeper than -1, when you do a plot of the ASKAP flies eye sample and your expected redshift distribution, you generally get peaks that zoom up towards Z of 0, right? This doesn't go infinite because it's not steeper than -1.5, but within 90% systematics range, you do get fits that allow a downturn, right? So it is not excluded there. So I just want to highlight that. And that's a fit, the corresponding fits to the DM, measured DM values. And you will see that we do, it's very difficult actually. It seems like the models tend to prefer more low DM ASKAP flies eye bursts that are not observed. I'll again get back to that later, but that's at, I mean, it's not statistically significant. It's at about 8% or something like that. So 1.5 sigma, but maybe that's a hint of something going on there. We'll see. Okay, and then the thing that about population evolution. So the best fit results, whether or not you use a prior on your spectral index or not, rules out no population evolution, right? We find very strong evidence that the FRB population is evolving in a way that's consistent with star formation, but it actually prefers a value that's more rapid than star formation, right? Up to star formation squared, right, with this power. So what the actual truth is, I don't know, but it is 100% evolving population, which I guess probably rules out models where you have a very, you know, let's say a merger model where you have a very long duration to a merger. Now we know that most bursts sort of probably come from repeats, and that is ruled out by cataclysmic models. But keep in mind here, what I'm modeling is this population observed by Parkes and ASKAP, which has been postulated to perhaps be a separate once-off population, right? And that part seems to be consistent with something that's going with a star formation, right? Which is consistent with young magnetars, right? You expect this to pretty much follow star formation. Now, what do we really detect? So, okay, this blue line here is the orange line from here, not the blue one. Sorry for the terrible choice. I mentioned this alternate model where the bursts are intrinsic narrowband, and that likelihood fit gives you the orange one here. Now, okay, maybe in maximum likelihood, it's not quite as good a fit as blue, but you know, these are not subsets of each other, right? So you can't do explicit tests on this one versus that one. But you can also model a simple, you know, do we actually observe this downturn, right? Because to say that you've detected something that evolves with the star formation rate, you're really saying, oh, extra bracket there. You're really saying that you detect not just this ramp up with redshift here, but a downturn with redshift. And the answer is that when you just get rid of this denominator and you model this part, right, 1 plus 8 to 2.17, you do not see any better fit due to that, right? So that's this green curve here. So you still rule out n equals 0, but you get an equally good fit. In other words, there's no evidence that we detect the downturn at high redshift because we're not sensitive to it. And so the main conclusion, which is this thing, is that yes, the FRB population is definitely evolving with redshift. It's consistent with the star formation rate, maybe a bit faster, but you know, we're not sure that we see a downturn yet. So we'll see. Okay. And I'll skip over the fits to the host galaxy DM contribution. I'll just point out that the best fit is a log mean of 145 parsecs per centimeter cubed. So a pretty significant amount, right? Which is generally more than you would expect from the Milky Way. But keep in mind here, host includes the local contribution from the bursts themselves, right? So here, host means the progenitor, the stuff around it, the host galaxy, the halo of the host galaxy, and even technically host here means everything in the cosmic web that is in excess of a random point that you pick in the cosmic web, right? So that's what host means. So, okay. So this is just to note that this is what you then get from your intrinsic DM distribution. In other words, if this is your cosmological contribution from, you know, ignoring the host as a function of redshift, if you add in the host contribution, this is the extragalactic contribution. This is what the distribution would look like. But okay, don't want to keep you too long. This is what I consider one of the more pretty plots, but this is the way I think we should think about the FRB population as a two-dimensional distribution in redshift and DM, right? So this is what would be probed. This is plotted for Parkes. Oh no, this is not. This is the ASKAP ICS sample, right? Because you can plot points in both redshift and DM, and this is the probability distribution, including all these biasing effects in redshift and dispersion measure. And this is 50%, 90%, and 99% of observations should lie within these contours. And what you see is that there should be some of order of 10% chance to see something in this distribution, which is a very large excess DM. We don't have anything in this very large excess DM distribution yet, except maybe you could argue actually this one, which is the slight under prediction. But we do get about half of them used in the sample lying in this region, half there, right? So my prediction is that at some point for these, we should get a localized FRB that's got a high DM but low redshift. We'll see about that. As I mentioned earlier, the tail of the log normal distribution in excess DM is not directly probed very well. So now, what about sort of my correlations? So this is for Parkes observations, right? This is exactly what I showed you earlier about the joint distribution of redshift and DM. And then you can ask, well, if this is your joint distribution of redshift and DM, what is the probability of a given redshift given a dispersion measure, right? So, well, as you expect, as you increase your dispersion measure, your expected redshift increases, and then it turns over. And the Makar relation reverses. Remember, this is not the theoretical, this is not DM given redshift, this is redshift given DM. So why did this happen? Well, let's look at the left-hand plot. You see here, as you increase in redshift, you get, most of your bursts, your median lies below your one-to-one relation because there's the tail in the positive direction is larger, right? So this is more like your mean, but your median is just below the mean here. And then at some point, you get to your maximum instrumental sensitivity, right? You're just unlikely, this region here, you'll only probe with Parkes if it's in the center of the multi-beam, of the primary beam in the multi-beam, right? So you're not that likely to see anything in this range, and you can't see anything beyond here. You then say, okay, if this corresponds to a certain DM of 1,800, what's the chance? How do you get a DM of about 2,400 or something like that? Well, you can't get it by going out here because you can't see that far in the universe. You can't get it by going up here because going up here means you reduce your sensitivity, and by definition, your max sensitivity anyway. So your only way to get an excess DM, above, let's say 1,800, is to go to the nearer universe and get a very large excess. And that means that at around this point here, as you increase your DM, your expected redshift will decrease, right? So this is telling you that for any large sample of FRBs, your highest DM events will not be your most distant, right? They'll actually be closer. And that if you were to plot things in order of DM, probably your most distant ones are still maybe the majority of your population will be here, but then your highest DM ones will be closer. Now, I'll skip over the example from ASKAP, but what I will point out here is that clearly this is all model dependent, right? But so what I've done here is this is for the ASKAP fly's eye observations. On the left are different estimates of the probability of joint distribution in redshift and DM for different parameter fits that are consistent at 90% confidence, right? So what I've done here is I pulled out the most extreme values of various parameters that you can get within 90% confidence limits. And you've got the joint distribution here and the probability of redshift given DM on the right. And sure, this turnover happens at different DMs and corresponding to different redshifts, but the turnover always happens, right? And that's simply because it's guaranteed. At some point, there will be a maximum distance out to which you can probe, right? Definitely. And therefore, the only way that you can get a higher DM than that will be to go to some excess DM, right? But the nature of the turnover is model dependent, right? But it's 100% guaranteed to be there at some level. So I'm going to skip over these two slides and just highlight something that isn't fitting too well. So this is the predicted redshift distribution of localized ASKAP FRBs, right? And no matter what I do, I can try throwing in a minimum FRB energy, which then gets constrained by Parkes observations. But you can see the best fit model is in orange, and the blue is the measured redshifts of the fitted data, right? And you see that these all cluster around like a medium value. And I always predict an excess at low redshift, which is not seen in the data. Now, this discrepancy is at about I forget what it is, about the 5-ish% level. So it's, 2 sigma-ish, okay, one-sided, so maybe, about 2 sigma-ish. If you start trying to introduce a minimum FRB energy, which does push in this direction, then you actually conflict with Parkes data. Because if you have a minimum FRB energy, then your nearest Parkes burst, would be less likely to be weak, right? If you have a minimum FRB, you say as soon as you see something that's nearby, it should be quite strong, right? So you start to conflict with Parkes data there. Having said that, within the gray points are the different 90% confidence limit variations and parameters, and you still can get a downturn there. So this, like I said, it's not super significant and might indicate that actually this parameter set could be better, but actually the other observations still favor this. So we'll see how we go with more ASKAP localized data. Similar-ish mystery, FAST has recently released a total of 4 DMs from their search now. And if you try to model FAST, this is what you get. Here's the 4 FAST FRBs, and these are the different model fits. And, again, with a minimum, your maximum. So this red dotted line is your maximum minimum FRB energy that you can get within about 90%. So, cumulative distribution wise, this does not look good. Your KS test will tell you, there's only 4 data points, but still, there could be something funny going on here. So these are my guesses to it. Option 1, it's due to repeaters. So sorry for all the text, but let's go through it. What I'm modeling is the total burst distribution, right? For any given telescope, for any given dwell time on one position, you look with any telescope in any direction for some amount of time, there's going to be a characteristic distance below which the average repeating FRB, whatever the heck that is, will produce more than one burst, right? So you take some average repeating FRB, you shift its distance, and for any given dwell time in any given direction, there'll be some distance below which you expect more than one burst, right? Now, above that distance, your burst distribution is basically the same, you don't care about if they repeat or not, right? It's the sum of the high energy tails of many repeaters. So you get Poisson stats in the burst rate. But below that characteristic distance, and clearly different repeating FRBs do different things, you get Poisson statistics in the number of progenitors, but a highly non-Poissonian distribution in the burst number, right? So you would therefore say that Arecibo got lucky in seeing one strong repeater in the volume of space it probed, and FAST did not. It also might indicate, as I mentioned, a turnover in the lunar velocity function, and maybe both. So these are the conclusions there. We've got some more accurate, precise parameter fits. This is compared to different other literature values. The modeling details do matter, right? So please, I think it's about time in this business that we started yelling at people who don't include these factors, right? I think we should be sophisticated enough to do so. The FRB population definitely does evolve with redshift, but exactly how is an open question. Predicting redshift from DM is difficult, right? And I would argue that using the models that use a one-to-one DM redshift relation I'll call it unreliable, right? Might be good enough, probably not, depending upon what they're using it for. I think some unlocalized FRBs are probably very likely quite nearby. The highest DM FRBs will not be the most distant. Oh yeah, I didn't get around to talking about the source counts distribution, but it's consistent with the potential downturn. There's still plenty of unanswered questions. And yeah, guys, putting CHIME observations to this would be great. So I'll leave it there. Thank you for tolerating a very long talk. Sorry that there's no, here's some new measurements. And I'll open it up for questions if any of you are still tuned in.
Excellent. Thank you so much, Clancy. That was fantastic and very, very interesting. All right, we can open up the floor for questions if people want to either speak up or use the raise hand feature.
I'll just get a bit more water, but I'll only be away for about 5 seconds and I can hear what you say. So please go ahead.
Okay, no problem. All right, so does anyone have a question that they want to kick us off with?
I have a question. Well, first of all, thank you for a really nice, interesting, very interesting talk. Appreciate the crazy hour that you're speaking at. So it's really nice of you. I think it was on slide 24, 25, where you showed the DM distributions, and you were asserting that they were almost similar and only 1.5 sigma different. But when I look at that, something looks totally wrong. So maybe I'm not understanding what you mean by 1.5 sigma difference. I think that might be it.
Yeah, so what I haven't shown here, come on, why can't I move it again? Okay, yeah, so essentially I did a KS test on this, right? And I could look up the exact number for you, but I think it may even be a higher fraction of the time. It's certainly not stronger than 1.5 sigma. You expect to find in the data, you know, a deviation from your curve that's this kind of deficit. So the other thing I did is I deliberately shown, so this one, the DM distribution for ASKAP fly's eye, and the, there's too many slides going, the redshift distribution for the incoherent sum observations. They're the worst matching features in the whole data set, right? So, you know, I'm matching DM and redshift and signal to noise ratios from ASKAP, Parkes, and ICS. And so the fact that when you've got these sort of 3 parameters and distributions from, well, 2 or 3 parameters and 3 telescopes, you're going to see something that's at this level of deviation. But I think it's clear that it's worthwhile speculating about the cause. But yeah, I'll see if I can, while someone asks the next question or you ask a follow-up, I'll see if I can find the exact results here. Wait a sec.
Well, I sort of did have a follow-up, but
Yep.
well, I mean, just that your conclusion that you know, the largest DM FRBs are not going to be the most distant because there's this turnover that you showed.
In any sufficiently large sample, right? If you've got 5, then that won't be. But if you've got, I don't know, hundreds or thousands. Yeah.
But I guess what I'm thinking is, oh, that requires that your host DM contribution be large enough that you could actually see such high DM sources that are nearby. So, you know, it must be covariant with what you assume for the host DM.
Yeah, I would say that.
And you got such a high value for that like, it makes me scratch my head a little bit.
Yeah, so it's not so much about the high mean host DM, because that's a well-fitted parameter, right? And even if you sort of say, okay, I've done fancy modeling, maybe it's dodgy. When you simply look at the mean dispersion measures measured by Parkes and ASKAP, you find that when Shannon et al. Did assumed about 100 DM for the host, then you would expect the difference between Parkes and ASKAP to be even greater, right? So you would have expected to do this. And the reason is that subtracting 100 DM was not sufficient. They should have subtracted more, which then makes a relative difference between the two. Okay. The dodgy part of that is we just don't have a very direct, so I've assumed a log normal distribution for the shape of the excess DM, and we just don't have a good direct probe for that beyond, you know, a DM excess of order 100 or 150, right? Like there's FRBs where we see an excess DMs of order 150 beyond the Makar relation, but we just don't have that many localized things. So it could be that, I mean, we know, right, that if an FRB goes off in a galaxy and then the line of sight goes through the center of that galaxy, right, if it was the Milky Way, we get an excess DM of 1,000, right? So it's clearly physically possible, right? And an FRB going off in the center of the Virgo cluster should get an excess DM of something like 2,000, right?
But if it went off in the center of a Milky Way galaxy that was edge on, yes, it'd have massive DM, but it'd have massive scattering as well.
Well, yeah, that's true. So there's various biasing effects as to why we might not be seeing those things. And you're right, like massive scattering is, that would cause all sorts of strange structure, is clearly something which might bias us away from seeing those. So I think, so to get back to your question, I 100% agree that the shape of the excess DM distribution, so let me pull up one of these figures here, right? So this is your modeled DM extragalactic, right? So this is cosmic. So let's say, I don't know, you accidentally line of sight passes through a massive halo plus host. And clearly this region up here, this sort of more than two, so this is your like 1 sigma thing. This region up here is not well directly probed, right? We just don't have all our localizations sit below this line. So the form of the distribution up here is not well probed. So quantitatively, right, what this looks like up here, right, slash what this looks like up here is still an open question, right? And the quantitative results are model dependent. However, the fact that as long as there's any population up here, right, and there should be, right, there should be at some level detected FRBs that go through a large amount of their host or something in the sightline, then the only way to get an FRB, about once you hit the maximum DM for your maximum sensitivity, then the only way to get higher DM is to go to a lower distance and a large excess. The question is what exactly the form of the turnover looks like. So it might be that only your highest DM 1% of your FRBs, or maybe even your highest DM 0.2% or something like that might obey that. But I would take a bet with someone on the highest DM China FRB that is not as far away as you think it is in either Canadian or Australian dollars.
Sadly, it's not well localized.
Yeah. But yes,
Right,
I think clearly we need a localized FRB that has some large DM, or just lots more localized FRBs that don't.
Okay, great. Are there any other quick questions? I think I see moving.
I have. Emily, can I ask?
Yes, please.
Awesome. Thanks, Clancy. It's a very interesting talk. So I have a couple of questions. I think one question is related to your parameterization of DM host, and but I think you said it's a little. It's not really. We are not really sensitive towards the lower end of the DM distribution, DM host distributions. I'll not ask that. But the second thing is
or the high end, right? So the low end we are sensitive to, but not the high DM host.
But how can you constrain the lower end? For example, the mean value you are assuming. How can you actually constrain that? For example, out of 13 FRBs, there are 8 or 9 FRBs with the DM host we think is smaller than 50 or 60 units. So in that case, in your DM host distribution plot, I'm not sure we are actually getting that, but this is something I need to figure out. But my second question is...
just to answer your question, the answer is this plot, right? So this is for the localized FRB sample, and these FRBs here all correspond to relatively low host DM, right? And clearly this one is constraining a minimum contribution here.
Yeah, that's right. So I'm just saying that in your final posterior values for mu and sigma for log normal distribution that you assume, it's really high. It's 138 and 0.50, thinking that most of the FRBs, localized FRBs, have lower host dispersion measure. Then how can we just get that high value? So that I'm just thinking about that. But my second question is,
keep in mind it's a log normal distribution, right? So essentially when you this variance that we get is about a factor of 0.5 in natural log, right? So at your 2 sigma level, then this 145 goes down to about 14.5.
Yeah, but we still expect around 50% of the FRBs have DM hosts greater than 110 DM units if I
Yep.
select 0.5.
Yep.
So this is something I'm just wondering, out of 13 localizations, if most of them actually say that the DM host has lower value. That's exactly what McQuart et al. Got in their analysis. Their mean is 50 and their sigma. So I'm just trying to understand that distribution. But my second question is, I think, pretty straightforward. So the question is, in 2019, they Vanch et al. They used they actually looked at Virgo cluster and they constrained the alpha value, or in your case, gamma value, smaller than 1.58, which is like 5 sigma, which challenges or like in at odds with your result by more than 5 sigma. So what is the
Yes.
possible explanation?
Well, the possible explanation there is one of the open questions I point out at the end, which is that, so for instance, at this, I find a relatively steep value of the source counts function. And if you extrapolate that to the Milky Way and things that are 10 kiloparsecs away, we should be getting a heck of a lot more galactic FRBs, right? So my almost certain explanation is that this steep, like it flattens off at some point. And then the question is exactly where is an open question, right? Because, yeah, it's for the reason you mentioned, that Virgo cluster observation is very much probing a much lower point in the source counts distribution. The other thing we should note, though, remember, is that looks at the total burst rate. So all my caveats, right, the closer you look in the universe, the more you're affected by did we get lucky and have a strong repeater in the volume? Yes or no, right? So I don't have a good idea about the distribution of repeaters in the universe, or rather I have lots of good ideas that are at most barely constrained by data. But that paper, if I recall correctly, modeled the burst distribution. And you could simply say, well, we know that strong repeating FRBs, or even not so strong repeating FRBs, are still pretty rare, right, in terms of a volumetric density sense. So I don't find it completely unreasonable to think that in the entirety of the Virgo cluster, they might not have any strong repeaters, right? I think, I don't want to assign a quantitative likelihood to that, but I think that's a genuine possibility. Because otherwise you just simply look out to Alpha Centauri and say, oh, we don't see anything there. Well, we get a constraint from that. But then you're limited by near universe statistics. You would do the same thing with AGN, right? We see with strong AGN, you get very biased if you look within the nearest 100 megaparsecs, because the strong AGN are rare, right?
Yeah, I think it's just that I think the total observation time that they have in their studies is like more than 300 hours. But related to your last statement, recently, I think it's Bohenek et al. They extrapolated, or what you say, interpolated the energy distribution function from what Low et al. Estimated, and they found that it sort of satisfies their volumetric rate of SDR 1935 plus 2154 like burst.
So
and
remind me which paper this was. Sorry. And when you also asked about this, the other caveat I want to put out is that, like I said at the start, and emphasizing the modeling. One thing I tried not to do was review every single FRB modeling paper that didn't take into account all these biasing and fitting effects. So I don't want to sound too harsh, but in my mind, every single paper out there that does not go through this process of taking into account all the different biasing effects, I'm not going to give too much weight to, right? I'm not going to utterly dismiss it, right? Because, there's clearly, as I mentioned, clearly the model that I have is not going to be complete.
Yeah, fair enough.
But there's a lot of things out there that are very wrong. Now, maybe this paper you refer to, which I don't think I'm familiar with, I didn't recognize the author name, maybe they do this, and so excuse me if they do take all these effects into account. But for instance, that Virgo paper didn't, right? there's, for instance, with the Virgo paper, a lot of those galaxies would have had a significant excess cluster DM that would have made you much less sensitive.
All right, so I think we need to wrap up, and we're a little bit over time. Sorry, everybody, but this was really interesting discussion, so I was keen to keep it going. All right, I will stop the recording.